H dot. Specifically, hydrogen atom. Right? H2, hydrogen molecule. H dot has the one nucleus and one electron. Right? That's H dot, hydrogen atom. Okay, H plus is a proton. H plus is composed of one proton and how many electrons there? How many electrons? Zero electron. Now then, what's the volume of hydrogen H plus? Nucleus size is 1 femtometer. It's very small, we said. And H plus does not have an electron. Then what's the volume of hydrogen plus, H plus? Huh?
원자핵이랑 무게가 부피가
Say again?
원자핵이랑 부피가 같을 것 같습니다.
원자핵이랑 부피가 같다. 그 말은 거의 부피가 없다는 얘기네. 갑자기 굉장히 이상한 걸 마주치지 않았어? All the time we said about the chemistry is a science for molecule, and we are handling the electrons. H plus is one of those most common species we meet. We are learning acid and base, right? H plus is very common. We see all the time. We feel we know that. By the way, all of a sudden H plus has no volume. All other species, they have a volume, but H plus does not have a volume. What's going on? Then H plus, if you shoot it, I have water here, oxygen to hydrogen, H plus comes in, it should penetrate, like a Rutherford experiment, because it doesn't have a volume. It's a very strange situation here, isn't it? Yeah, the name is a proton, and majority answer says a proton. But that is quite a strange species, so it may not be the realistic shape. So the next question is, this is a hydronium. It sounds like the name-wise, hydronium sounds like H plus is a hydronium, right? Ion is a potassium, sodium is a positively charged one. Oxonium, ammonium, it was a plus, right? But hydronium sounds like a hydroium is H plus, but hydronium is actually water complex of the proton. So this is realistic situation in water environment. H plus is difficult to exist. It's just one nucleus. That's why it is attached to water molecule. For convenience, we say H plus, but most likely it is the form of H3 plus form. And the name of it is hydronium. Okay? Or more specifically, hydroxonium is the more specific name, but it's a little abbreviated. So current standard name of that is hydronium. Okay? Hydronium is not H plus. It's a water complex. H plus is a proton. It's a very strange species, just a nucleus, like an alpha particle of a helium nucleus. Hydrogen nucleus is a proton. Okay? And we said neutral positive charged one, then negative charged one. Okay, very good. Negative charged one, I. So we learned ammonium, ammonia, amide, right? Oxonium, oxide, OH minus, and chloride, fluoride, bromide, all those negative ones, usually IDE. So this is a hydride. Hydroid has a 1 proton in the center as a nucleus. How many electrons there? 2 electrons. Okay. Still, that's okay. We have the atomic orbital layered, and then 2 electrons they can share. It's a relatively stable species, not difficult to find. H minus, it can exist as is. H plus is very strange. No electron should be compressed with water. Okay. So this is the basic names. We didn't learn it, but I felt that this is good to know as a basic knowledge to move on. Now organic molecules. Okay, we already have studied this. This carbocation should have sp2, right? sp2 orbital should be a planar structure, right? So there is a review. One more time review. Okay, that should be sp3. That's why it's a three-dimensional tetrahedral structure. They may compete to each other, but eventually the number of available electrons, they determine which one is more stable. That's why radical, CH3 radical is in between, we said, right? But a little more close to planar structure. Okay, now based on that, new thing we learned. Okay, that's something we have learned. The three atoms, and then 1 pi electron, and something attached to that. And then this position can be either positive or neutral or negative. So that position, even though there are 2 electrons, here 1 electron, 2 electron, here 2 electron. Here anion should be 2 electron too. But in this case, this pi bound system, they make particle in a box kind of model, and they have a connected sigma bond and then pi bond exists. Next to that position here, this position tend to participate in this planar structure, and then filled 4 electrons, means this system has a layer and then 2 electron on the bottom, 2 electron on top. So this is kind of a planar structure, and this is the basis of most of those resonance structure we have drawn. Okay, even though it has filled electron, 2 electron there, extra electron, totally that's a 4 electron system. But if you draw that molecular orbital, just fine. They filled up the 2 the electron layers, and then this is a whole planar structure. All together, this is similar to like this. When we draw the resonance of this, 5 electron and one of the electron species here, comparing to this is a higher electron. That's why this donate, and then this moves, and the resonance structure of this is this. Looks like a symmetric in both sides, right? Electron movement is from high electron density to low electron direction. That's why they moved like this, but they are on the same plane. And that position is also sp2 character in there. Okay? All 3 electrons are sp2 character. Similar situation, but one electron is missing. One electron here. Now, neutral, 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 3 electrons here. So which one has a higher density is difficult to say. That's why they provide one electron half ahead. One electron goes this way, half ahead, then resonance structure is like this. So that means even if they can distribute, they didn't really donate. One electron each donate and then make a new bond here, and then this is radical. Okay, same sp3 structure, that's why planar. And electron number is the 3 electron systems. Okay. 그래도 고집세네. 계속. Now we have a 2 electron system. Positive here, and no electron here, 2 electron here. 3 atoms, but 2 electron. Now, which one has a higher electron density? This one is higher than this, right? That's why resonance structure. Now, this is a full head, and the structure will be like this. So we just discussed about this in the last class, but this is a little difficult, the concept, and difficult to capture. That's why I wanted to review one by one. 3 electrons are together, and one of them is a pi electron. Regardless of the number of electrons for the third atom, positive, negative, neutral means 0 electron, 1 electron, 2 electron. Anyway, all of these, they behave like same system, and then they move around. Okay, from high electron to low electron. If it's neutral, then anyways it's sharing, and all 3 are occupying sp2 structure, planar structure. Okay, this system name is allele structure. If it's all carbon, that is called as allele or allelic structure. That is maybe most difficult part of when you draw the structure. It's kind of a mixed of the structure. Okay, but this is a quite important one, something you may see all the time in organic chemistry. Okay, last problem. Okay, very good. Now this is the structure with the CH3 here. The big difference is before, previous ones, everything was a CH2 structure, and then there was one empty orbital there. And whether that empty orbital is a filled or not, if it's a filled, anion. Empty, cation. Just a radical, is a neutral. Okay, but once this is occupied by 3 bonds, now this is a stable sp3, and they do not share. So this is kind of an isolated pi electron. Okay? Only when this third position has empty orbital, then they can participate here. They make kind of a delocalized structure. So this is sp2, this is allelic structure. Okay. 오, 진이가 좀 빨랐네 오늘. Okay, based on this, if you review quickly about the resonance, now if you look at those resonance structure, now we can realize that this resonance structure is similar to that allelic structure. This is pi bond, and then this is a third atom, and now this is a positive, the negatively charged. means this has a more electron. This is similar to allylic anion, right? Then this can donate, you can draw, this can donate electron here and push up and make this resonance bond. Very similar to allylic anion. Right? So all the situations, this one is similar to radical situation. All connected together, not allylic, but in this case, everything is all neutral, they can move around. So this is the resonance structure. Similar situation here. Base treatment, deprotonate. Remove proton, that's the base. Then the end result is anion here, pi electron here. So pi electron system, anion, almost a similar situation, right? This can donate and push out. This makes this kind of resonance. So previous case, everything was a carbon, 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 carbon. In this case, it doesn't matter, any atom comes in. Anyway, if this is a pi electron, then they can behave as planar structure. All three atoms are on the same plane, and then they share those electrons. If it's so, this is the general the picture of it, and this is the anion case. This can be shared this way or this way. Two directions it can go, and it has more the resonance structures. From this way, and it can form this resonance bond. Go this way, then it can form this resonance bond. A little extended version, but basic idea is pi electron connected to another, the sp2, the atom. If it is a radical, then now this is situation, this is similar to radical situation, then half arrow move in, then they can make intermediate this structure and this structure. Okay, so this was the resonance. Most of the resonance we have learned is composed of one pi electron, and then next position is either taking up if it is positively charged, or donate if it is negative. Okay, that was the resonance structure we have seen. Okay. Okay. After this, we have learned about classical acid and base. Classical acid and base. Jaehyun? Okay, Jaehyun, could you explain what is the classical definition of acid and base? What is acid?
아레니우스 정의로는 산은 H 플러스를 내놓는 분자고 또 염기는 OH 마이너스를 내놓는.
Okay. So proton, the donator is an acid. Hydroxide donator is a base. That's a very classical Arrhenius, the definition. And you mean? What is the next definition? Second? Brensted-Lowry definition wise. Proton donating one is acid, and base is proton acceptor. Even though there is no OH minus is generated, proton donor and acceptor concept, that's a little more extended and covering more examples of acid and base. Okay. Today we are going to study even further extended, which can cover all the cases of acid and base. Okay. Even though there is no proton donating, still we can define some species as an acid. How do we do? By this concept. If there is any electron donating species, electron donating species is a base. So coming back to the center of chemistry, we explain the concept with electrons. Okay? Electron donating is a base. Electron accepting is an acid. And they can have this kind of a donor-acceptor relationship, and then they can have this kind of bond. And this is acid-base. It can explain all the cases, including the previous the definition of a Brensted-Lowry or Arrhenius cases. So in this case, there is no proton, no OH minus. But in this case, we can see this magnesium, the ion, is here, and then these oxygens, they donate the electron, and then magnesium or the ion, they can accept that electron and make this kind of a bond, temporary bond. It's not covalent bonding, that's why they draw not solid line, they put dotted line. It's kind of a bond that's reversible. Covalent bond is usually quite stable. Once it is formed, it's difficult to break. For the breaking of a covalent bond, what kind of energy do you need? How much energy do you need to have, Kyungmin? How much energy do you need to break the covalent bond? Carbon-carbon bond, so-called bond dissociation energy. Single bond, 100 kilocalorie per mole. Okay, at least the unit is also important because there is another unit, kilojoule per mole, that's much lower, right? So kilocalorie per mole, about 100. So that kind of energy is required to break covalent bond, right? So comparing to that, it's a little weaker, especially in the water environment. It can be much easier to break the bond, so they put this kind of dotted line. Anyway, to make this bond, the donator is this oxygen donated electron. That's why that electron, that oxygen, is considered as a base. Metal ion, it accepted that electron. That's why this one is we describe as acid. This is a little difficult, different from conventional acid-base definition. But this can cover all the cases. Now, if you think about another case, oxygen, they have a lone pair electron. They can donate electron. And boron, where is boron in periodic table? Hydrogen, helium, lithium, beryllium, and boron, right? So this is quite this side. This side is a more metallic area, right? This is non-metallic area here. So boron is like a metal. That means it is electron deficient. And carbon has 4 electrons and it can form 4 bonds. Boron has 3 electrons and it can form 3 bonds. The problem is now with the 3 bonds, it has only 6 electrons around. It does not meet the octet rule. So that's electron thirsty. They want more electron. Okay, that's why boron is a typical acid because they wanted to take more electrons to occupy the 8 electrons in there. That's why they behave as electron deficient species and attract this electron from this lone pair electron to this, and then forming this kind of a bond. Now, once you form this bond, now you need to give these formal charges. Originally, both of them are neutral, but this one donate that electron to this guy. That's why boron, the end result was boron occupied extra electron, one more electron than nucleus charges. That's why we designate there -1. And oxygen donate 1 pair, but bond-wise is only 1 bond, so 1 minus. That's why it becomes 1 minus of electron, that's why it becomes positive. This was the formal charge we have practiced, right? So as the end result, they can form this kind of a temporary bond, and we designated this one as a base, this one as an acid. We can see the general examples. Let's say if it donates the proton, so this is a conventional classical acid, right? So some acids we see proton donator. Alcohol, water, they can donate the proton, even though that's a little weak acid. Carboxyl acid, it can donate the proton, it's a stronger acid. pKa of water, do you remember? 16, about the 16. pKa of carboxyl acid, about the 4, 5, but let's say to be simple, carboxyl acid is about the 4. Okay? Phenol we didn't learn, but phenol is about the 10. So then, which one is stronger? This one and this one. Carboxyl acid and phenol. Which one is the stronger acid? Carboxyl acid is a stronger acid. 4 and 10, right? How many folds stronger? 4 and 10, 10 minus 4 is 6.
100,000.
Second,
100,000.
100,000, 10 to the 6.
Yes.
It's a 10 to the 6
No. Million.
million times, right? So 4 and the 4 and 10 is a 6 difference. One difference is a 10, right? Because it's a log scale, log 10 scale. That's why 4 and 5, 10 times. 4 and 6, 100 times. 4 and 7, 1,000 times. 4 and 8, 10,000. 4 and 9, 100,000. 4 and 10, million times. So that means comparing these two, this is very strong acid. This is a quite weak acid. And water is now 16 to this guy 10, that's another million times. Right? Water we consider that's a neutral, almost a neutral. Water is at the 16. Phenol is a million times stronger acid than water. Carboxyl acid is another million times the stronger acid than phenol. 기억하기 좋지. 4, 10, 16 이 정도 넘버는 머릿속에 들어있으면 필요할 때 딱 꺼내가지고 비교해야 된다고 비교해서 바로바로 쓸 수 있으면 되게 편리해. 안 찾아봐도 요 정도 숫자는 물어볼 거야. Carbonic acid 4, phenol 10, water 16 이 정도 외울 수 있겠지. And another example of acid, as we just have seen, metal cations. Metal cations, they donated electron, they become positively charged. Lithium, sodium, potassium, this line. And second line, magnesium, what's next? Calcium. So this is second law. And these guys, they donated those extra electron. They have 8 electrons on the valence shell, but anyway, they are deficient of electrons. They are happy to attract more electrons. That's why they act as acid. Okay. Not only the ions, if the metal makes the stable bond with its partners like this, and this complex is difficult to dissociate. Still, if you look at this bond, Al and Cl, aluminum is more electropositive than Cl. Chloride is more electronegative. So that means this one take more electron. If this is a 1 unit, then aluminum should be 3 delta plus, right? Donate some electron this way, and this way. This is electron deficient. So in a sense, these two lines look quite similar. Metal cation or kind of metal cation character it has. Okay, those guys act as acid because they are electron deficient. With this example, if I ask you lithium metal Li0, is that acid? Lithium 0, it's not acid because it is neutral. After it donates electron, it becomes cation. Now they become acid. Similar situation is here, right? Formal charge wise, this one is also aluminum should be +3. Okay, those are acids, electron deficient species. Base, okay, water. Let's see. Then this definition really covers those conventional acid. Now, if you mix together HCl with water, then this oxygen donate electron, it forms this hydronium ion, okay, or oxonium ion. So hydronium ion, H3 plus. You don't see H plus in this picture. H plus, as I said, is quite strange species. Usually we don't see. It's just the nucleus. Okay, they exist as this kind of form. Now, if you look at this, now this itself, H3 plus, H3O plus, this is also acid. So there's a two equilibriums. It can donate a proton, and this can donate a proton too. This is stronger acid, and then equilibrium should be shifted to this way. After this, it can donate this proton to the other partner too. So this is a cascade, one step, two step, cascade the proton donations. This is kind of intermediate. And in this case, now proton, if you think, proton, no electron, but positive charges. Is it electron rich or electron deficient? 일렉트론이 많아, 일렉트론이 부족해. 일렉트론이 당연히 부족하겠지. It's the positive charges on the metal H+. It's similar to lithium plus, sodium plus. In the sense, H+ is acid. It's the smallest the atom in periodic table. That's why the speed-wise, H+ is the fastest. Light particle moves faster. That's why electron is moving even faster than nucleus. Right? Proton is the fastest atom among all the elements because that's the lightest. Atomic weight is only 1. Right? So that's why proton is acting as very important acid. And another reason is the environment is in the water. H2O itself is a proton source. It's a weak acid though. That's why H+ is a representative acid. But we can explain that with electron deficiency or richness. Proton, H+, electron poor, electron deficient. That's why it can act as acid. And it can be explained not as a proton, electron deficient species as acid. Okay, that's a Lewis definition. Now base. Base is electron donating guy. Then they should have electron rich species. Representative one, oxygens. And sp3 oxygen, sp2 oxygen, which one is more acidic and more basic? Which one has a more electron density? sp2. It has a more S character. More S character has a little richer condensed electron density. So compared to this one is a stronger base. And sp3, sp2, 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 sp3 together, sp2, sp3 together. Now nitrogens. Nitrogen has longer electron too. Comparing to the nitrogen and oxygen, which one is a stronger base? Alcohol versus ammonia, which one is a stronger base? Ammonia, because it is nitrogen. I explained this to you one time. Anybody can repeat that? Why nitrogen is a better electron donor than oxygen? Don't ever let. 다 가르쳐 준 거를 다시 물어보고 또 통전으로 꼬셔야 된단 말이지. Who wanted to explain this?
문자 번호가 작아서 양전화가 더 가기 때문에
원자 번호가 작으면 양전화가 더 강한가?
작아가지고 나이트로젠 이제 전자를 더덜 자연스럽고
다시 한번 정리해서 얘기해볼까?
지수가 문자 번호가 작기 때문에 이제 전자를 더 잘 잡고 있을 수가 없어가지고
이거 정리해서 말하자면은 이제 옥시전이랑 나이트로젠이랑 비교했을 때 이제 나이트로젠이 훨씬 더 일렉트론 네거티비티가 작기 때문에 이제 결합을 이뤘을 때 훨씬 더 산소보다 이제 전자를 붙잡고 있는 능력이 약해서 이제 훨씬 더 LCD에 전자를 줄 수 있는 능력이 더 좋다고 생각합니다.
두 사람 다 맞는 설명을 했고 크게 두 번째 대답이 첫 번째 대답보다 다른 것 같지는 않으니까 여기서 하나 첫 번째 디스코를 주는 거잖아. Nitrogen and oxygen. Nitrogen has a lower atomic number or lower the electronegativity. And actually, it's rather than electronegativity, that's more atomic number because that is about the nuclear charge. Okay? Nuclear charge is smaller. That's why even though it has a one electron pair here, attracting force to the nucleus is only one time. Then oxygen case, it has a one more charges on the nucleus. That's why it has a stronger attracting force. So those two electron pairs are more attached to the oxygen. It's more difficult to donate. Okay. That's the explanation of why nitrogen is the stronger base than oxygen. And this is a very important concept. You can utilize this other idea to explain many different things. Electron on nitrogen is more flexible, more movable, more donatable than oxygen. Even though it has two electron pair, this is one electron pair. This one electron pair is more donatable. That property we call basicity. Okay? So that's oxygen to nitrogen, and oxygen connected to other part. Anyway, these are naturally occurring bases composed of organic molecules. Okay. Now let's look at this molecule. What's the name of this molecule? 너무 시세에서 답하기 싫어 여기나? Acetic acid. Okay, this molecule, acetic acid. Now, last time we have seen anion of this acetate. Acetate has a two resonance form, right? Two resonance form. Now, this oxygen versus this oxygen. Then if I put this hydrogen up to here, then is that also resonance form? Acetate case, we said that that's a resonance. Actually, it's kind of 1.5 bond, like benzene, right? Now, acetic acid. Now there are two oxygens. The two oxygens here, they are equivalent or not? In acetate case, those two oxygens were equivalent or not? 함정이 안 빠지려고 조심하는데. 정빈아, what do you think? Let's simplify the question again. In acetate, okay, anion, acetate, those two oxygens, they are equivalent or equivalent means it has same charges. Of course, it can be exchangeable. Acetate. Equivalent, yes. That's how we explain as a resonance. In this case, acetic acid, proton is attached. And proton is attached, can attach to here and here too, right? If you draw those lines, electron donate here and push it up, and the proton is attached to here. Those two structure is equivalent or not? It is not equivalent. It's a different. And that's why this electron here, this is sp2 character. This electron here, this is sp3 character. And those two electrons behave differently. And two molecules attached, the proton moves from here to here. That's also a different structure. Here, even though the carboxylic acid is acid, if you add even stronger acid, like a sulfuric acid or the HCl, then proton donating power is even, these guys have stronger acids. Proton can be donated here, and that proton can go to sp2, the oxygen. Now, proton. Now this is the opposite case of acetate, right? Acetate, we removed one proton, made it into anions, and it was resonance form, right? 1.5 charge each. 1/2, half charge each. In this case, protonated here, and this is positive charges here. Now this one and this one, they are similar situation to acetate, and these are equivalent. And this is a resonance structure. Now we can push that electron movement, this lone pair electron, again, pi bond and one atom attached to that. Then previously it was a neutral negative charges. Then we flow this electron this way, right? But in this case, this is a positive charges. Then neutral is more electron density than positive. So that's why this electron can be donated here and push. Then if you draw this way, then this is perfect resonance structure. And if you draw that line here, then this is plus charges distributed over 3. This is resonance structure, but this is not. If you put this proton up to here, now that's not we call resonance structure. Then in the case, what do we call that relationship? If it is not resonance, then how do you call it? These two relationship is not resonance. Those two oxygens are not equivalent. These are isomer, very good. These are isomer, and if they change their structure back and forth, then that back and forth situation, what do you call? Two species there, they can toss. In this case, electron is moving around. In that case, electron is also moving, but at the same time, which one is moving? Proton is moving. Proton was here, and that proton is moved here. This is kind of isomer, very good. This is equilibrium. 평행 발음, 평행. And how do we distinguish equilibrium and resonance? And notation is also different. Notation-wise, that resonance notation was this, right? This is a resonance. This is equilibrium. In your textbook, sometimes they draw this way, but anyway, it's the same. Okay? This is equilibrium. So how do you distinguish whether this relationship is equilibrium or resonance?
레저넌스는 이제 일렉트론 덴시티 차이에 의해서 전자가 이동하는 것이고, 아이소머 같은 경우는 그림에 있는 경우는 이제 일렉트론 덴시티의 차이는 아니지만 이제 아예 구조적 차이가 프로톤을 포함한 구조적 차이까지 볼 수 있기 때문에 그걸로 구분할 수 있을 것 같습니다.
조금만 더 다듬어볼까? 구조적 차이라고 하는 것은 뭐가 움직였다는 얘기죠? 프로톤만 그럴까?
프로톤과 일렉트론 둘 다. 아톰 자체.
프로톤 혹은 atom. This is a very important point. Resonance structure, only electrons are moving. There is no atomic movement. If actually they are same structure, both of them, the real situation is in between somewhere here, right? That's why nothing is moving. Just for conveniency, we put double bond here and single bond here. So that's a resonance. That's only for convenience, like a formal charge. It may not present the real situation. Real situation is in between here, like a benzene, right? Resonance, the equilibrium or isomer. Isomer is a very stable, or it can be relatively unstable. They can move back and forth. Then this kind of situation we call this is equilibrium. And in this equilibrium, atom should be moved. In this case, proton is moved. So this relationship is isomerization. And I said this is a special isomer because only proton moved. Proton is the lightest one. That's why proton movement is the easiest. That's why this special isomer we call tautomer. And that's one kind of isomer. Only proton moved isomer we call tautomer. And that isomerization we call tautomerization. Okay, that's a special isomer relation. Anyway, protein is also atom. That's why atom moved. Then you should not put this. You should put this. Okay. 말없이 간단하게 썼지만 이 기호가 나타내고 있는데 많은 의미가 들어있는 거야. 그 의미를 알고 써야 되는 거고. Here, the electron movement is also starting point is from electron and moving to ending position, and starting from electron position to ending position, and full head. Full head means the two electrons moving, and where it starts and where it ends. That's very important. If you draw this picture, something like this, I would feel very uncomfortable because electron source should be here, not here, right? Proton is electron poor part. There is no extra electron to donate. The electron should start here. If you draw this like this is also uncomfortable. And the result should be double bond like this. So this is landing position. Okay? So this small positioning is also very important. That represents how much you understand, at least those premise we described, those electron movement. Okay? So this is the big difference of resonance and deuterium. And you don't want to draw this way, because in this case, here this electron is more the basic than this electron. So proton, if they exist together, they should go to sp2 electron first, not here. Okay. Now, similar situations, even though it's not acid, if there's any carbonyl group, that carbonyl hydrogen lone pair electron should be electron donating. You can donate this electron to proton and catch it. Proton acted as acid because that accepted electron. That oxygen donated electron, that's a base. So even OH minus, H plus, they can be explained by electron movement. That's the Lewis definition. Then you can cover all the cases of acid and base. Now, if you have this kind of structure, so-called imidazole. Imidazole structure, it can act as both acid and base. Now, if you look at here, you can donate NH's proton can be donated, and that can act as acid. This nitrogen, it has a lone pair electron here. It can accept electric proton. So it has the two motif in the same molecule, acid motif and base molecule. Water is the same. H2O, it can donate proton, it can accept proton too, right? Water acts as, at the same time, weak acid and weak base. Now, this kind of situations, we learned about the dipole. Dipole, if it's just a transit molecule, lithium plus, is this dipole? What is a pole? Yubina, is this dipole? Dipole means how many poles there? Two pole, right? This means two. This is the monopole. So if it's just a charged point, then we don't call it dipole. Dipole means somehow charge is separated to two positions, like water. Then this is dipole moment drawing, right? So this behave like this. So charge is separated in one-dimensional space. That's a dipole. If it's moved to 4 direction, quadrupole. 6 direction, hexapole. Okay. Now, if you have this kind of partially separated structure through electromagnetic force, they tend to align this way. If they align this way, negative, negative, they will push each other. This is the unstable structure. If you just mix them together, they will align anyway. If there's a permanent dipole there, dipole will be aligned. And if it has a bigger molecule like proteins, positive charge this side, the negative charge this side, they will stack like this. Plus, minus, plus, minus, plus, minus like this. Stack. So that's kind of the driving force to form macromolecules in natural molecules. So water molecule, if you look at water molecule, it has partially negative here, partially positive here. If I put one dipole, then just direction this way, right? One dipole, the other dipole, but if you do fragment, otherwise. Oxygen is slightly negatively charged. Proton should be slightly positively charged. So there is one dipole here, two dipole there, right? Combined dipole is this direction, but oxygen here, two proton here, moving is this way. Positive, positive, two negative here. And this proton, as we said, water can donate this proton as acid. And it can, and also this oxygen's lone pair electron, it can accept proton. So then, this oxygen, this water donate this proton to neighboring water, and this proton even can jump up to the other oxygen. If it is not fully given to the other one, still this is a partially positive charge, partially negative charge. That's not plus 1 plus the minus 1, but still that's, let's say, plus 0.2, 0.3. Still there is electric attraction force there. So they can be aligned this way. Oops. Aligned this way. Similar way, ammonia, also it has a lone pair electron, stronger base, can donate, and another ammonia can donate this proton. It's not stronger acid, but anyway, it can donate this one too. So this structure is very the funny way. Water molecules are there. Usually we draw H2O, 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 but they don't exist as a separate water molecule. Only after it is evaporated, they becomes a gas molecule. The water molecule may be hang around. If it is in the solution, in liquid status, they make this kind of a big network, and it's almost like one oxygen to two hydrogen ratio big network, not single molecules, because this proton is always jump around. For convenience, we draw H2O. Okay, majority of them is H2O structure maybe, but real structure is making this kind of a network, and their network is electromagnetic force by dipole. That's why their interaction is quite strong to each other comparing to neutral molecules. Neutral molecules, they don't have attracting force to each other. That's why water molecule has quite high boiling point. They hold themselves very strongly, and this special bond. Last time we said in molecular level, only one force we consider, electromagnetic force. If it's a charged species, sodium chloride, +1, -1, that's obvious, 1-to-1 interaction. It's not +1, but this is maybe +0.2, -0.2. It's a little weaker, but still, they can attract to each other. Less than sodium chloride, but water to water has quite strong interactions to each other, mediated by proton. Proton is a sharing, like acid-base reactions all the time, making big network. This kind of a special cases we call special name as hydrogen bond. Hydrogen bond actually we should call proton bond, but by convention we say hydrogen bond. Hydrogen bond is the interaction of molecules utilizing proton as acid, proton as a mediator, and then sharing those proton partially here, and then they stabilize themselves. This is a special interaction we call hydrogen bonding or hydrogen bonding. Which atom can make a hydrogen bonding? They should have base motif. Also, they should have a proton source. Element-wise, nitrogen, oxygen, and fluorine. Majority, there is some minor one on the bottom, but those three: oxygen, nitrogen, fluorine. But fluorine, only example is HF, fluoric acid. If fluorine is attached to the carbon, it does not act as hydrogen bonding the donor, hydrogen bonding acceptor. Because comparing to nitrogen, oxygen, fluorine, they have 3 pairs of lone pair electron, but attracting force is even bigger than oxygen. So then those lone pair electron is very tightly bound to the nucleus. They don't have a power to donate. That's why F is usually ignored. Only HF. So then hydrogen bonding oxygen and nitrogen. That's the main accessory atoms on organic molecule. So if you see nitrogen, oxygen, those are hydrogen bonding acceptor. If they have proton attached to them, that's a hydrogen bonding donor. That's a special case we call hydrogen bond. And they act as a very important role of this DNA structure. DNA has one strand and the other strand. And we have heard DNA is composed of ATCG, 4 different bases. And then they attach to each other. That force is hydrogen bonding. So here, A and T, they have a hydrogen bonding donor, acceptor pair, and they bind to each other. They hold each other and make this big double strand process. So AT has a 2 hydrogen bond. CG, they have a 3 hydrogen bond like this. Which pair may be stronger? CG pair or AT pair? CG pair may be stronger because it's 3 hydrogen bonding. Right? It's like a Gliber effect. Gliber. Even though it's a small force each, but there's many binding, then they can make a very strong structure like this to form up this kind of bonding. Okay, so this is basis of the DNA double helix structure utilizing hydrogen bond. Now, small example here, one alcohol, the other alcohol. If you look at these 2 molecules, even though we didn't learn much of this organic molecule, it's vitamin A, vitamin C. Which molecule looks like a more hydrophobic? Which molecule looks like more hydrophilic? Okay, which one is more hydrophilic? Vitamin C, right? Because it has a lot of OH group here. Looks like they can form more hydrogen bonding. So when you say hydrophobic, hydrophilic, hydro is water, right? Hydrophilic, like water, means this kind of a hydrogen bonding forming ability. So NH2, OH, you have a lot of them. They are polar and hydrophilic. If it's non-hydrogen bonding structure and just hydrocarbons, they are considered as hydrophobic or lipophilic. Okay? So this is basic character we can see. In nature, we have acid as a carboxyl acid, COOH, as an acid structure. Base, usually they contain this nitrogen. Now, basic element of organic matter molecule, so carbon and hydrogen, and accessory wise, oxygen and nitrogen. Oxygen case, COOH make acid, pKa 4. Okay? And base wise, these nitrogen containing molecules are usually act as a base, natural base, instead of NaOH, hydrogen artificial base. Okay? Those base has this kind of nitrogen, and this nitrogen containing molecule all together as a class, they call alkaloid. Alkali is a base, right? But the kind of molecule we call alkaloid. Oid is a similar, humanoid, human-like, organoid, organ-like, alkaloid, alkali-like. Okay? So those hydrogen-containing molecules, they are called as alkaloid or base, natural base. Means hydrogen-containing molecules usually act as the base. Okay, so this is end of the second chapter, acid and base. So next class we move to alkane, not yet, alkane. Now this is the some basic structure of alkane. Saturated hydrocarbons. So the one carbon, methane, ethane, propane, butane, kind of a naming. So next class you will study about this numbering of these. Also about those isomers. So here methane, how many isomers there? Methane's molecular formula is CH4. Can you think any other isomer based on isomer? What is isomer? Same molecular formula. Toxic has a different kinds. Experimental formula, molecular formula. So we say molecular formula. Same molecular formula, but with a different connectivity or different spatial orientation. Okay. So methane CH4, no other isomer. Ethane C2H6, only one form. Propane C3H8. How many isomer there? No isomer. Butane C4H10. How many isomer there? 2. Can you draw them? Who said 2? 2. 나도 한번 걸어볼래? 이렇게 그리지 말고 뼈다구로만 그려. 스켈레터 스트럭처로. 좋아. 2. 그거 말하고 하기 너무 섭섭하잖아. How about 5? 펜테닌. 두 개인 것 같아. 누가 더 버틸 사람 있어? 버텨봐. 뭐야 저거? If you draw this way, then molecular formula becomes different. This one C4H10, this one C4H8, C5H10. Molecular formula is changing. Then that's another isomer. Yay, nice. So here, butane, isobutane, normal pentane, isopentane. Iso means equivalent, similar, equivalent. This is a neopentane, new pentane. Can you draw the isomers of a hexane? Hexane has a 6 carbon and C6H14. 각자 한번 그려봐. 몇 개나 그릴 수 있는지. 이야, 시스테마틱하게 막 한다. 더 없어? Are you sure? 맞아, 잘했어. Okay, as you can see here, only 4 carbon, 5 carbon, 6 carbon. Already you see there are many combinations there you can make. So this is very important, the practice too. So next class will be next Tuesday, not Thursday. So assignment 2, I will give those assignments, already I put it up on the PLMS. So that assignment due is a Thursday. 그러면 먹을 수업은 어떡하냐고? Thursday class you will study online. So I put up all of the study material on PLMS. You will see some video and you will see some problems set there. And there is special assignment there too. So textbook problem solving will be by Thursday morning, and then you study those materials through PLMS, and then that assignment due day is next Tuesday, and no class on Thursday here. We'll meet again next Tuesday. Okay. For this the assignment, you will the practice with this hydrocarbon drawing and numbering system kind of things. Okay. Okay. And you will study about the oxidation and reduction, and I put up that question here too. So you will study 3 topics on Thursday using PLMS, the video material. Okay. 목요일날 수업 없어. 혼자 공부하고, 숙제는 오늘 숙제는 목요일 아침까지, 이날 숙제는 그 PLMS 숙제는 다음 주 화요일 아침까지. 숙제에다가 이름만 써서 내라고 하는데 굳이 어사이먼트 몇 번 쓰고 이름도 빼놓은 사람도 있어. 내가 소심하게 복수할 거야. 이름만 쓴 사람 점수 안 줄 거야. 이름만 써, 이름. 자, 성도 붙여서 써야 돼.
토요일 날 수업은 좀 실시간인가요?
내가 그냥 녹화 한글로 올려놨으니까 가서 하나 때 정도 하면 돼. 실시간으로 안 해도 돼. 오케이? 수업은 여기까지. 질문 있으면 질문하고.